Hi, I'm Nick Krzyzewski,
And I'm Renee St. Louis.
and we're from the Cake Lab at Worcester Polytechnic Institute, and we're here to discuss our paper, Quantifying and Improving Performance of Distributed Deep Learning with Cloud Storage. So, as I'm sure all of you know, deep learning is exploding right now, both in industry and in academia. But if you don't have a cluster available to you, you might have to turn to something like commodity cloud storage, such as Google Cloud Platform or Amazon Web Services. And as we make that transition, we're going to have to consider what assumptions we make in the on-prem case that we may not necessarily be able to apply to the cloud. For instance, you may not be able to store training data on each node in the cloud like you may be able to in the on-prem case, because storing data on each node actually has a per gigabyte cost. And on-prem, you might just have that storage space available to you because storage is pretty cheap. In addition, in the on-prem case, we're actually also able to configure our network in such a way that we're able to make inter-node communication pretty efficient. We're able to, you have high performance NICs, high performance switches, and then configure that in a way that may be beneficial to us. But in the cloud, you kind of just got to work with what you're given, and that may not necessarily be good enough for something high performance like distributed training. On top of that, on-prem, you may choose to have a centralized store for your data. And again, you're going to run into the same kind of problems with latency and whatnot, online in the cloud that you wouldn't necessarily have on-prem. One upside, though, is that cloud bucket stores, for instance, actually scale automatically. So prior research is focused on trying to reduce the load on these centralized stores, but because of this scaling, you actually may not have to worry about it as much. Lastly, we want to talk about serverless architectures and other things like that may not be able to store the data on disk to train from. You actually may need to rely on a centralized store, like a bucket store. For instance, in serverless, there's ephemeral storage that's very limited, so you may not be able to store very much in it. Or make good use of it. So you really using a centralized store may be a necessity, and we want to find a way to optimize that case so that you're not just wasting a bunch of time making fetches. And this brings us to our key problem of how can we store training data in cloud storage and still train with similar performance as if we stored it on disk. So some of the benefits of storage buckets, as I mentioned, they're super scalable and they'll scale automatically. Which is great because we don't have to worry about provisioning or anything like that. But as we venture into these applications that may require them, it's going to be hugely beneficial. And in those cases, or even not in those cases for that matter, they're super cost effective per gigabyte. If you store in a Google Compute Engine VM, it costs 4 cents per gigabyte per VM to store there. But if you look at object storage, it's actually only 2 cents per gigabyte, no matter the number of nodes that are accessing it. So it actually ends up looking like it's going to be quite a bit cheaper. There is an asterisk on that 2 cents once, and we're going to get to that in a little bit, but it turns out the cost is actually a little bit more nuanced than the per gigabyte cost. But the per gigabyte cost ends up seeming like a good option for you to be able to work with it. But there's obviously, there's no free lunch. And cloud bucket storage has a serious catch, which is that the performance is really not that great. Like we mentioned, the networking in these cloud environments may not always be optimal. We found that loading data, a set amount of data from disk, this was actually MNIST data set. In a micro benchmark, we found that on disk, it took about 40 seconds, but as we moved to the cloud, it got about 100 times worse. And this, the bucket storage just really isn't effective when you have to have this performance that's so much worse. The other downside is that these buckets don't actually let you fetch batches of samples at once. They actually will say you have to make one request at a time serially. So what we actually did was we spun up 16 worker threads, and we tried to run this experiment again, and we found that the performance actually, it improves quite a bit compared to the sequential case, but it's still not nearly as good as disk, and the cost savings end up really not being worth it because you're going to spend more and more time on compute at that rate. So how do we get to an optimized solution? We're going to analyze how to best make use of cloud storage buckets as a way to store training data. We're going to quantify the performance of using cloud storage for training. Past research actually tends not to focus on the data loading pipeline of deep learning. They actually tend to focus on overall training performance. And we really wanted to isolate that part of the pipeline. We wanted to look at how we can improve just the data loading time and, and actually increase overall performance as a result. Through this analysis, we built a prototype that will be generally efficient for fetching from cloud storage buckets.
And that brings us to our solution, DELI. The two main principles that DELI operates on are prefetching and caching. Essentially, because, as Nick mentioned, cloud network traffic is so slow and expensive, we want to avoid waiting on I/O whenever possible. We want to fetch data before we need it so that when we're ready to train on it, it's right there and we can get going without waiting. And on top of this, the best way to speed up fetches is not to make them in the first place if we can avoid this. And we can do this by caching fetched data ahead of time and aggressively maintaining it so that we can train on it when we're ready to. This is represented by a simple diagram that we have of what we like to call the full fetch approach. Two important metrics to define here are the cache size and the fetch size. The cache size is however many samples can fit on the cache that you have on each node at any given time. And the fetch size is the number of samples that we're going to fetch all at the same time. Here in the full fetch approach, we set the fetch size equal to the cache size. This means in effect that we start with an empty cache. And as soon as we start training, we're going to fetch an entire cache's worth of data. We start training on that. And once our cache is depleted, we make another fetch. As you may guess, this is pretty simple and naive, but not the best that we can do. We've played around with different ratios of the fetch size to the cache size, and through them all, we've found that the best is what we like to call the 50-50 approach. In this, we set the fetch size equal to half of the cache size. Again, we start with an empty cache. We fetch one fetch, which is half of the cache, and then anytime the cache dips below half full, we make another fetch. So in this case, we immediately fetch again to get an almost full cache. We train on this until our cache again dips below half full, at which point we make another fetch. The cycle continues, so on and so forth. Because we always have at least half of the cache or at least one fetch in the cache at all times, we will always have data to work on. And this is the most that we can have our fetch size, such that another fetch can always fit cleanly into our cache. This is the best configuration we have found, and we will show results on its performance later. This system diagram gives an overview of how DELI works. Up here, we have the data store of our Google Cloud bucket. These big rectangles here are the different nodes that we're training on, and the leftmost node has been enlarged to show the mechanisms at work within it. Here we have a few PyTorch components that we have unmodified as denoted by their PyTorch logo. We have the sampler, dataset, and the data loader. On top of those, we have some components that we designed or wrapped around the PyTorch components, such as our dataset, sampler, and our prefetch service. So when we're actually loading data, our training loop will ask for data from the data loader. The data loader contains a dataset and sampler. The dataset takes in indices and produces the samples corresponding to those indices. It'll ask for those indices from our sampler, which produces a stream of indices. The sampler wraps a subsampler that, again, is written by PyTorch and would be whatever sampler you were using beforehand. So if this produced samples sequentially or randomly or due to some custom algorithm that you define, it works with our system. Our sampler will pull out the next long list of these samples equal to the fetch size and return the first few of them to the dataset. At the same time as it does this, it hands the entire list to the prefetch service. The prefetch service will try to retrieve the samples corresponding to these indices from the data store and cache them as soon as it can. All of this happens asynchronously with the rest of the system. This isn't waiting for any input or confirmation from any other components. And this is to ensure that it can run as fast as possible and that we are prefetching as much data as we can as fast as we can. While all of this is going on, the data set has received the samples it needs from the sampler, and it's trying to get the actual samples corresponding to those indices from the cache. If we get lucky and the samples were cached in time, then it retrieves them and hands them back to the training loop. If the samples did not arrive to the cache in time, then we default back to the sub-data set that we are wrapping, which if implemented right, will retrieve the samples from the data store. The reason that we allow this to happen and that we don't wait to make sure that the samples are in the cache first is to make sure that we are always getting the samples that the user requested to the training loop in the fastest way that is available to us at any given time through any network connection or conditions. This ensures that we are training as fast as we can with whatever is available.
So how does the system perform? In order to measure this, we had an experimental setup of 3 Google Compute Engine VMs, each outfitted with 2 Intel Haswell vCPUs, 13 gigabytes of memory, and 1 NVIDIA K80. The independent operation of our system actually allows us to be a little bit looser in our choice of number of nodes. So we have 3 here, but the trends should relatively remain the same no matter the number of nodes. And indeed, in some of our preliminary experiments, we were able to confirm that this did have this was the case. However, just for our purposes, we actually defaulted to 3 nodes in each training configuration, all working in a distributed data parallel fashion. Each experiment ran on ResNet 50 with CFAR10, or a relatively small convolutional neural network with MNIST, each for 2 epochs. There are a couple of reasons for this. One, we wanted to be able to look at a relatively complex and a relatively simple model. And then 2, the number of epochs was chosen because some prior research shows that after the second epoch, performance will generally level off. And indeed, we were able to confirm this through some preliminary experiments. So for most of our experiments, we actually just went ahead and ran 2, and we're able to use that to represent the first epoch and the later epoch cases. So if we analyze the cases of fetching from disk, just looking at the data loading time, which is the time that it takes to read from disk and to prepare it for training, not any actual training. For MNIST, we see about 150 seconds in reading from disk, and for CFAR10, we see about 200 seconds. The second we go ahead and start reading from the cloud buckets, using it naively as if it were a disk that we could just fetch from, with no problems, this time skyrockets. It ends up being almost 800 seconds in the worst case, which really isn't acceptable. We saw that some models that took 10 minutes to train from disk took 3 hours to train from the cloud, which was not great. The second we add caching in, though, we start to see some gains. This is actually just a very simple cache of, once we fetch a sample, say it's sample 10, asking for sample 10 won't require going to the storage bucket. On the first epoch, as you can imagine, there's nothing in the cache, so we actually don't see any benefits at all. But as we get to the second epoch, working probabilistically, you're only going to end up in a 3-node setup getting about 33% of the same samples again. So we end up losing performance that we could theoretically have gained. It's just not that great compared to the disk case. But once we go ahead and add prefetching into the mix, things get a lot better. We can actually start talking about this in terms of being comparable to disk. However, you'll notice that this still uses an unlimited cache. And unlimited caches, if they were feasible, we wouldn't necessarily need to be doing this research at all. We could just store all the data on disk and have it not be a problem. So we want to be able to optimize for that. And so instead, we look at using the 50-50 approach. The 50-50 approach necessitates that for a fetch size of 1024, we have a cache size of 2048 samples. And so, we actually do start limiting ourselves here. And to that end, we do actually see some better performance, though, despite limiting the cache size. And the reason for that is that, as we explained earlier, that when you do prefetching with the 50-50 approach, there will always be some data made available to you, which will increase performance. You'll also note that one of the cases here actually has slightly better performance than working from disk, and that's because of some of the optimizations that our cache, MongoDB, actually makes. And that may not necessarily scale as you have larger and larger data sets, but the general idea should still be the same. They are going to have relatively comparable performance as if you just read from disk, which is pretty exciting. So now we want to drill down into this case a little bit, into these cases a little bit. First, we want to look at how adjusting the fetch size affects performance. You'll notice here we're using the miss rate as our metric instead of the data loading time, and that's because we wanted to be able to normalize between data sets that may be different sizes or have a different number of samples or something like that. And so this actually works as a pretty good normalization technique, because what we found is that the miss rate correlates linearly with the data loading time. And we can see here that just simply increasing the fetch size will always increase performance, which is pretty great. And I mean, it makes intuitive sense. The more data you fetch ahead of time, the less you're going to miss from your cache. To actually focus not on the prefetching though, and on the caching though for a second, we found that as you increase the cache size, you don't necessarily get performance gains. Just because you're allocating space doesn't mean that you necessarily are going to make use of it in an effective way. And so it's just after a certain point, it's not beneficial. But what I really like about this plot is because it has a batch size of 1024 and a fetch size of 1024. And after we've had our fetching of only 1024 samples, which is just our batch size, we actually maintain pretty optimal performance. You only have to store the batch you're currently training on at any given time to have good performance, which I think is a really powerful takeaway from all of this. It's just such a small amount on disk at a time can be really, really great. And lastly, we want to look at how the 50-50 approach actually benefits us. We can see that for MNIST, it's actually not too much of a benefit. It goes from the miss rates don't really change between switching these approaches. But for something long running like CFAR 10 on Resonant 50, because it's such a complicated model, the compute time is long enough that the prefetcher actually is going to have time to fetch more data while the compute is going on. So we actually do start to see more and more performance gains, which shows us that as we start to work with these more and more complex models, we can actually get more and more benefit of prefetching, which is really exciting. So lastly, we want to talk about cost. Cost is something we started out this presentation with to talk about as a saving from buckets. And it's not as great as we would have hoped. We look at this table here shows some baselines that didn't use DELI at all, and some components that actually use DELI. And we see that only in a couple of cases do we actually see any cost improvement. And those are really in cases where we have longer times for the compute to be taking place. There are some improvements we discussed in the paper that could actually improve this even more. But regardless of those improvements, even this is still promising. And if nothing else, you do still break even, which is something that is still promising, if nothing else. So to wrap things up, we want to just to emphasize that we can drastically improve the performance of training from storage buckets just with a couple of simple classical techniques, just like prefetching and caching. And our approach shows some promising, though not necessarily definite, cost effectiveness. And the reason that's so great is because we can actually still use these improvements in these alternative architectures like serverless, and not lose money in using them. We actually, even if we were to just break even, the improvements are still applicable to these other cases, which is really, really exciting. And it's something that we're really happy with as a takeaway from this work.
We've open sourced all of the code that we wrote for DELI at the repository shown. This repository also contains all of the experimental results that we derived from this. If you would like to build on or examine any of that, we encourage you to. We'd also like to thank our advisor, Professor Tian, without whom none of this would have been possible. Thank you so much for all of the help and guidance that you've given us through this process. It's been amazing. And lastly, to everyone watching this video and engaging with the cloud computing community, thank you.